We're going to take a look at rational expressions. We have a smaller set of lectures this week because rational expressions can take some time. So plan on investing a little bit of extra time this week just for the algebra with these functions. So we're going to take a look at defining them. We're going to be able to do some basic operations with them with multiplication and division, and we're also going to talk a little bit about reciprocals. So to define a rational expression, a lot of people think, well, they're fractions. Well, that is partially true. It's an algebraic fraction, which means it has to be the quotient of two polynomials. So something like 1/4 is not an algebraic fraction, it's a numeric fraction. So then that doesn't apply. Something that we want to keep in the forefront of our mind the entire time we're in this lesson is that a denominator can never be equal to 0 or it's going to cause it to be undefined. So we want to make sure we really call that to the forefront. So a rational function is, again, it's defined by that quotient of those two polynomials where the bottom can never be 0 because that's going to result in something that's undefined. So how does that relate to domain? Well, if you remember when I talked about domain, I said sometimes we play devil's advocate and we have to figure out where does it not exist so that we can then write the domain expression of where it does exist. With this, with rational functions, we are going to set the denominator equal to 0, and those are all the values where it's not going to exist. So we're going to write the intervals where it does. So we're just going to pull out those specific values in the domain. So let's take a look at one. Here I have two polynomials, and it's asking me to give the domain and set builder and interval notation. So I'm really just looking for where is this denominator equal to 0. So I'm going to set it equal to 0. You're going to have to pull those factoring skills back from last week and factor it out and then solve. So I know at -2 and 3 is where this graph does not exist. It exists everywhere else. So I can say that in two ways. I can say it in set builder notation, which is x is a real number, meaning it's every single value, except x cannot equal -2 or 3. Or I can write it in interval notation. So when you do interval notation, you always start with negative infinity, and you're going to go to the first place it doesn't exist. It doesn't exist at -2. That's the smallest value. And it's going to exist from -2 to 3, the other value it doesn't exist at, and from 3 to infinity. So it's like you're doing gaps. And the reason we're using parentheses is because it can't be exactly equal to -2. It could be -2.1, -2.001. So that parentheses is just telling us we can't be exactly that value. Here, if I want to give the domain in that set builder notation, you might kind of get stumped in the lab because it's a 5. And 5 can never be 0. So therefore, there's no value the domain doesn't exist in. So it's going to be from negative infinity to positive infinity, and we have to use those parentheses. So let's look at how do we reduce these. We can reduce fractions, so how do we reduce rational numbers? Well, a rational number is going to reduce in the same way. We're going to cancel factors. So if I had 3 times 5 over 4 times 5, the factor 5 is in common in the top and the bottom. So I would cancel them out and it would become 1, so that I'm left with 3/4. We're going to apply that to rational expressions by factoring, dividing out the common factors, which means canceling. So if I have this rational expression, I'm going to factor the top and factor the bottom. I'm worried about the top because I want to reduce this, not because I want to find domain. So I'm going to factor the top and the bottom. They each have a y minus 1 in common, so I'm going to cancel out those factors, and I'm left with y plus 3 over y minus 2. Now, if they were asking you for domain, you would still set y minus 2 and y minus 1 equal to 0, because either one of those values will cause a 0. If they're just asking you to reduce, then you can cancel and be done. But always check domain first, then reduce. Here's another one. I'm going to factor the top and the bottom, but y squared plus 4 does not factor because I have to have subtraction of perfect squares to be able to factor it. So this is the lowest terms already there. If I have 1 plus p cubed over 1 plus p, that factors from last week on our sum of cubes, and then we're able to cancel the 1 plus p, and we actually wind up with something that's not even rational anymore, right? This is just a plain polynomial. So that can also happen in the lab. Here I have r minus 1 and 1 minus r. So what I could do is factor a negative 1 out of the denominator so that I can then cancel my factors and my answer is negative 1. This is a really tricky one that does come up in the lab and it does come up on the test. So just quickly jot a note down that when you see this style, you can go ahead and do that factorization. Here, I'm looking at this, and that bottom is a special factoring formula. I'm going to be able to take a negative 1 out so that I then have the sum and the difference of squares. And I can cancel out so that I'm left with 1 over negative p minus 2, or you can leave the negative 1 in the front. Now, the quotient of opposites is an interesting situation. When I have a quotient of opposites, they're going to be negative 1 always. So this is just a shortcut. This is the exact same thing we did on the other page, but it's just giving you a rule that's going to work every single time. If you're not good with keeping track of all these rules, I definitely don't want to you to try something new with this, or you to try and cram it in. You can do the same thing by factoring out the negative 1. So how do we multiply them? Well, we know how to divide them. We factor and cancel. To multiply, you're going to do the same thing. You're going to factor, then you're going to apply the fundamental property and multiply. Then you're going to check your answer to be sure it's in lowest terms. Lowest terms is going to be what probably gets most people in this section. So I would factor the top and the bottom. Then I'm going to cancel out anything I can cancel out. Notice that even though I'm multiplying across two fractions, I can still cancel the c minus 2. That's okay, as long as they're top and bottom. Then I can still cancel the c's, so all that I'm left with of that huge polynomial is c minus 2, c minus 1. So really, when you're multiplying rational expressions, it's no different than dividing them. You're going to factor, then you're going to cancel, and you're going to simplify. So it's not really like you're doing a whole other function. If I want to find the reciprocal is just the flip. There's a technical explanation about the product being 1, but at the end of the day, it's a flip of the fraction. So let's look at it. If I have this expression, to divide two fractions, I have to flip the second one. Look at that, it's flipped, and it becomes multiplication. Then I'm going to factor, I'm going to cancel, and I'm going to simplify. So when you're doing division, you're going to turn it into multiplication, flip the second fraction, factor, cancel, and then simplify.